A little bit about myself before we start. I'm from Argentina. This is my first conference outside South America, as both as a speaker and as an attendee, so I'm pretty excited about that. I work coding and researching different things at MoveIt. We had a booth, so I talk with some of the guys here. If you want to find me on the internet, those are my GitHub and Twitter profiles. So if you're wondering a little bit about MoveIt, we are a software consultancy firm. We are based in Austin, Texas, Uruguay, Argentina, and Colombia. We work on a lot of different technologies, languages. We build a lot of different things, from mobile apps to websites and everything. We have our first Node.js/React.js apprenticeship on Austin. We do that periodically, so if you are from Austin or you know someone from Austin that might be interested in learning Node.js or React.js, just check our site and see how that's going. That's our Twitter. So before we start, I would like to make one disclaimer. This was originally a 1 hour long talk because a broad topic, and I need to fit them in 25 minutes, so bear with me on some things. I hopefully will get through everything. So a lot of people ask me today, why Node.js for machine learning? Especially because there are a lot of languages that are well known for being performant. They have better libraries for data science. Python has TensorFlow, Scikit-learn. R has a lot of math libraries, as well as MATLAB. My answer, personally, was that after ES6 came out, I'm using JavaScript for everything. All my prototypes and everything is JavaScript. But if you want to, talk to your boss about using JavaScript for machine learning, you should go with this explanation. We do web development, so it makes sense for us to use Node because we are already using Node. We know the ecosystem, package manager, and everything. So it makes sense. It was easier to onboard people because they already know ES6, they already know JavaScript, and they already know everything about the framework and a little bit about the theory, so you don't need to explain TensorFlow or distributed computing or extra things that you don't really need for the case. We all love JavaScript because we are all here in a JavaScript conference. Node.js has a lot of modules that are great for different things, like normalizing our data, working with our output, and a lot of just general things. We have modules for everything, so that's great about Node. The first one, the right tool for the job. Well, for me, it worked because I'm not ingesting the amount of data that Facebook or Instagram are using or ingesting. So for me, it makes sense. It's working now in production. Some of my products, I had recommendation systems and a lot of things working. They're fine. Don't have any CPU issues much. So that's pretty cool. So yeah, what's machine learning anyway? I was trying to find a definition or something to put in here, and I found this quote from Arthur Samuels. He's a pioneer in artificial intelligence. He said that it's a field of study that gives the computer the ability to learn without being explicitly programmed. And this quote is interesting to me because it draws the difference between what's called weak AI and strong AI. Weak AI, you can think of that as when you code a program to play chess or checkers. As a user, you get the impression that the computer is actually thinking of how to beat you, or the computer will learn how to play. But actually, it's just following a set of steps that you pre-program, like paths or brute forcing or whatever. But strong AI, it's when you program the mechanism for the computer to learn to do something, and it's up to the computer what they do next. So that's kind of what's interesting and hard about machine learning. I'm linking here to a paper from Arthur Samuels about game theory and AI. And that's a pretty good article about the difference between artificial intelligence and machine learning. So if you want to check those out. There are different kinds of learning. The first one is unsupervised learning. This type of learning is when you have a bunch of data that you know nothing about, that maybe you're mining from your application from other places, and you just want to try to figure out patterns or some way to group that data. For example, maybe you have a bunch of data from your users, like their weight and their height, and you just move things around, and then you figure, hey, so all these guys are size S for T-shirts. This old set of guys are medium, and so forth. So that's kind of what this kind of learning is about. It's pretty commonly used for data clustering and data mining. And then we have supervised learning, which is more widely used, which is basically learning by examples. You will have a set of data, labeled data, so you know what that data means, and you're going to feed that data into your model, and your model is going to try to figure out a function that can learn different patterns about that data. So basically, that will help you to solve a lot of different problems. Some problems that supervised learning solve, it's classification problems, which is basically you taking an input, and you need to classify that input among a set of labels. For example, an input being a picture, and a set of labels being that's a hot dog or it's not a hot dog. Or regression problems, when you try to predict some continuous numeric output based on an input, for example, trying to figure out the price of a house based on the size of the house, or trying to predict your score in a test based on your previous scores. That's a regression problem. There are a lot of different types of algorithms. Those are pretty popular, but there are a bunch more. I have been using all these in JavaScript. For the first four, key neighbors, classification and regression trees, support vector machines, naive Bayes. There's this package called machine_learning. They have implementations of all of them. So if you want to just play around, you can download the package and throw inputs and see what happens. If you're interested in how the algorithm works, you can just go to the source and check the files. They are fairly small, and it's pretty interesting to just research and check how those are built. And that paper, it's about like a brief description of every single algorithm. I think there are more than those. And why would you use one over the other, and just like use cases in general. Just pretty cool. So I'm on time. I'm going to try to do a brief introduction to neural networks in JavaScript. I'm going to use this library for the examples. It's called SynapticJS. How many of you have heard about SynapticJS? How many of you are using SynapticJS? OK. So this library, for me, it's great. It works on both the browser and Node.js. It was created by this guy, Juan Casala, which is from Argentina. He has a lot of examples, a wiki with a lot of examples. Everything's pretty well documented. So just getting there was just a breeze, getting from trying to learn machine learning in Python. I was raising issues, like asking super noob questions, and they were super polite, like, yeah, you need to do that, or they were explaining everything to me. I was pretty great, so go and give him stars or ask him questions. It's good. There is another library called node.js, which started as a fork of Synaptic. Then they built their own thing using backpropagation and neuroevolution. So this is more for kind of gaming things. It's more performant, but if you just want to play around with things, I would recommend start with Synaptic and then move to node.js. So every time I think of neural networks, that's the picture that everyone that has in his mind, like about nodes and arrows. And that doesn't really explain what they do, but what they basically do is split data into groups. So what you're trying to get the computer to do with a neural network is, hey, computer, could you split this data in different groups? It's like, sure. It splits the data into groups, and then you have a new entry point of your data, and you can just see where it fits, and that's like the classification of the regression problem. So starting from like the basic unit of a neural network, obviously it's a neuron. I won't draw the parallelism between this kind of neuron and the real neurons, because I really don't know how neurons actually work, but I know how this works. So Yeah, a neuron basically is composed of different parts. We have these arrows coming into the neuron, which is the red dot right there. These arrows are called synapses. They could be an output from another neuron or just your input. Every single one of these synapses or the arrows are a value, which is your input, and they are all multiplied by a weight. That weight at first it's random. And the whole thing of machine learning, especially in neural network, is just finding the weights that make sense for your data to get the input, the output that you want. Then all neural networks, besides their inputs, they have one extra input called a bias, which is always 1, and it has its own weight. And this bias, what it does is ensure that even if all the inputs are 0, you're still going to get some kind of output. That's why that's a 1. It has also random weight assigned to that. Then the neuron has an activation function that we're going to see in a couple of slides after this one. And then you have the synapses going out of the neuron. That could be your final output, or it could be the input of the next one. So the activation functions, what they do basically is grabbing all the inputs from the neuron. They add them together. The inputs of the neuron are basically your inputs or the input of the output of the previous neuron multiplied by the weight. And the activation function grabs all the inputs, add them together, and then use that as an input for itself. SynapticJS by default uses logistic sigmoid functions, which basically maps every value that you use as an input between 0 and 1. That's basically what it does. If you want to know more about like the theory, I linked some papers there and some an answer in Quora that was pretty well explained. There are some other activation functions. I'm playing with rectified linear unit now a lot. I didn't use the other two. And I know NepTopic has even more. But Sigma, it's pretty popular, and you don't really need to change that unless you notice that your use case is not like working. So you can play around with the functions and trying to see what it's better for your use case. But starting with Sigma, it's totally fine. So a neuron can perform these 4 different operations. They can project, they can activate, they can propagate, and they can gate. Project is basically setting a synapse between 2 neurons. That's the red one is projecting into the blue one. They can activate. That's when they grab all the inputs, add them together, and call the sigmoid function with that value. They can propagate, which is the actual training of the neuron. That's when you get an output from the neuron that wasn't what you expected. So you propagate back the error based on what you really expected. And that's going to change the weights of all the synapses back to the first input neuron. And that's what's called backpropagation. And that's how the neuron learns. And finally, they can gate. That's an operation that's not pretty common. It's just for one kind of neural network that if we have time, we're going to see later. But yeah. This is a small example on Synaptic on how you can create this neural network based on 2 neurons. We create 2 neurons, A and B. We project A to B. That's the synapses between those. And then B has an output. Then we activate A with 0.5. Then when we do that, A sends through the synapse 0.5 times a random weight first, and then we activate B. B grabs that output from A, performs the sigmoid activation function, and we get like a lot of random data because we are not really doing anything. So if we wanted to train B to output 0 every time that A activates with 1, this is how we do it. We do the same thing than before, create the 2 neurons, we project one to the other one. We set up a learning rate that will be important for our propagation. And then we have a for loop that's our training session. This training session has 20,000 iterations. And on each iteration, it does the same thing. Calls A, activate 1, then activates B. We don't care what B is at this moment, what the output of B is, because we are going to propagate that error. So we say every time we activate A, you should propagate B with 0. So what we are saying here is every time that A is 1, B should be 0. And the propagate will change the weights like 20,000 times until we get closer and closer to 0. So when the training session ends, we activate AB1, and we get that something pretty close to 0 that you could do a math from. And that's the training of your first 2 neuron-based neural network. Obviously, on real neural networks, you will need like a bunch of different neurons and layers. And this is how a real neural network looks. You can see on like why you should use a number of hidden layers and how many neurons that hidden layer should have based on those. There is a paper right there, and a Stack Exchange link that explains that very well. So let's build a small neural network as an example. You are, I guess, all familiar with the XOR operation. What it does basically, it takes 2 inputs. If the 2 inputs are equal, they output 0. They are different, they output 1. So we are going to train a neural network to perform this operation. So based on this picture, we can say, OK, so we have 2 inputs on our vector. So it's going to be 2 neurons on the input layer. We have 1 output on our vector, so it's going to be 1 neuron on the output layer. And then we usually had at least 1 hidden layer. You could not have any, but that's just for super simple classification problems. And at that point, you might not need neural networks. I mean, you can use them, but it defeats the purpose. But yeah, let's use 1 hidden layer. And the rule of thumb for selecting how many neurons should be in the hidden layer, it's basically the mean between the neurons on the output layer and the input layer. So in this case, 2. So going on Synaptic again, we import the layer object, the network object. We create our 3 layers. Ignore that 3 right there, that should be a 2. Then we project 1 layer to the other one, the input layer to the hidden layer, the hidden layer to the output layer, and then we create the network using the network constructor. So we have a network. It looks something like this: 2 neurons on the input, 1 on the output, and our hidden layer. And this is how our training looks. We are going to use a learning rate of 0.3. This is like my starting point for every learning rate. Then I tweak that, I play around with that until I get the output that I want. And that's kind of how it works, unless you have a PhD and you know what you are doing. But that's how I do it. Well, again, we have training session of 20,000 iterations. And we say, OK, every time that we activate our network with 0 and 0, I'm expecting a 0. 0 and 1, I'm expecting a 1, and so for it. And that will loop 20,000 times. Now, if I can get console to work, I can do this is, for example, how it works. It's pretty fast. It's a small example. And you can just play around with that, like saying 1 and 1. And that will put some 1. Yeah, I will upload the code for the examples later on my GitHub. But yeah, this is how you can build a simple neural network. One thing that you might notice is that all the inputs are numbers between 0 and 1. So if you want to use like real data that you probably want to, you need to perform normalization. That means all your data should be mapped into values between 0 and 1. I had an example for that, but I had to cut that off. So go to Synaptic. They have a great guide about data normalization. Yeah. There are some other types of networks. We have convolutional neural networks. These are mostly used for image recognition because if you try to use a regular neural network like this one, like with an image, you will split the image into pixels, but then the neural network won't have the context to make sense of those pixels because it needs a spatial context. So that's why what this neural network brings into the table. You can see that link explains everything pretty well. This is based on how the animals actually see pictures. So it's pretty interesting if you are into those things. Then you have recurrent neural networks. These are neural networks that fit themselves with their own output. So this is for trying to find patterns on sequence of data. Basically, if you are like trying to teach the neural network the alphabet, you will need to know which letter was before the one that you are doing now. And that loop does that gives that little context. Then you have another type of neural network that it's still recurrent, but this one keeps, it uses that gate function on the neurons, and it keeps track of things that happened a long time ago. This is used when you want to teach like a neural network to write like Harry Potter. You can make the network like read all the books like 20,000 times, and then it's going to remember, yeah, so every 5 characters I use a space, I say Harry this many times between each word. And there are a lot of cool experiments with that. You can just go on that link and see there are a lot of people doing a lot of interesting things with this kind of network. So I have a couple of final notes. This is like my main node. I experiment a lot with Node.js and just with every model that I found. And I really like to encourage people to do the same because I didn't knew that we had so many modules for machine learning until I started like dig them on NPM. So I think everyone should just go and play around with Synaptic and make your coworkers aware that that exists because maybe they want to learn about this and they don't want to learn Python or math or TensorFlow. So no, it's pretty cool. And also, there is a quote that I heard on the ErlangConf a couple of weeks ago saying that if you are employing people, you should give them time to experiment because otherwise they are going to experiment in production. You don't want that. So that's another note. I know there are people that's concerned about the performance of JavaScript in all these things. So my answer is check GPU.js, HamsterJS, GPU.js, self-explanatory. You can access the GPU with JavaScript. That solved a lot of my problems with like huge amount of training data. I just connect a GPU and use that. If you don't have GPU, you can use HamsterJS, which is native threading for Node.js. That's also solved a couple of problems for me. And yeah, if you want to play around with neural networks and you don't know what to do, there are libraries for IoT like Journey5, Cylon, and you can use that as inputs on your neural network and start doing like weird things, And there is Robot.js, which is automation for the desktop on Node.js. You can just feed a recurrent neural network with the movements of your mouse and try to recreate your session. I mean, you can experiment with a lot of modules. So that's pretty cool. And like last thing, I have a lot of meetings with clients that they say, yeah, I want this machine learning algorithm to predict stock trades or to be rich or something. And it's like, yeah, that's not how it works. I mean, when you're working on machine learning, your product is not actually the machine learning algorithm because everything is open source. There are papers for everything. If you want to build a neural network that learns to play music, there is a paper for that. There is at least 100 guys that implemented that in different ways. So the product is the data. If you don't have data, the neural network, it's just not going to work, or it's going to work poorly. So if you are working on machine learning things, your real product is the data. My last advice, follow this guy. He posts a lot of things for machine learning for normal people like me. So I understand that. So you can understand that too. So thank you for having me.